Good evening, everyone. Welcome to NPTEL tutorial session for the course Classics in Total Synthesis. So, today is our eighth week tutorial session. So, in the last few weeks, we were discussing some of the lecture contents which were taught by Professor Krishna P. Kaliappan in his 7 week lectures, and we have discussed the mechanisms of several reactions, and we have discussed the assignments and related questions as well. Okay, so we were here in the last session. So we have discussed this week 5 assignment. So today, firstly, we will see the next week lecture contents. That is week 7 lecture content about reserpine and then quinine. Then we have seen yohimbine and then robin. So these were the and morphine. So these were the topics for the week 7 lecture contents. Okay. So the reserpine total synthesis by Woodward involved this application of Diels-Alder reaction, Bischler-Napierski reaction in the total synthesis of reserpine by Woodward. So reserpine, as we can see from the structure, is a pentacyclic compound and it's isolated from dried root of snake root, which is used in the treatment of snake bites. So the first total synthesis was reported by Woodward in 1956, and it is one of the most complex natural products of its size. Five contiguous chiral centers are there out of the six total chiral centers, and 21 atoms are arranged in five rings. Six-membered ring is attached with another six-membered ring. So these all are the structural features with cis ring junction, as we can see here, these two, and this could be constructed via Diels-Alder reaction. So the key reaction involved in this are MPV reduction, benzoquinone, and Bischler-Napieralski reaction. Now, in the next lecture, we have seen this total synthesis of yohimbine, where this application of Diels-Alder reaction in the total synthesis of yohimbine by tamaline and intramolecular Michael addition in the total synthesis by Momos. So, this same chord structure is present here as well as that of reserpine, and it was isolated in 1880 from Corinanda rohimbi, and the first total synthesis was reported by uh, Van Temelen in 1958, and it was a racemic where the symmetric was done by resolution, and it is almost similar to Woodward's total synthesis of reserpine, and the starting material used are butadiene and benzoquinone, and tamaline synthesis was completed in 20 steps where he completed it in 0.024 percentage overall yield from Diels-Alder adduct. So in Momo's total synthesis, which was completed in 1990, which is the first asymmetric total synthesis. And the key steps were asymmetric intramolecular Michael reaction, where the starting material was protected benzylamine, and it was done in 13 linear steps with 25.6 percentage of overall yield. Now, in the next lecture, which is about quinine, the first formal total synthesis of quinine was reported by Woodward following Reip's protocol and Stokes asymmetric total synthesis. So, this quinine and quinidine are cinchona alkaloids, which was isolated from the bark of Cinchona and Remigia species, and it is used in the treatment of fever. So, quinine is used for the treatment of malaria, and it is having antipyretic, anti-malarial, and analgesic, and anti-inflammatory activities. Though quinine was not structurally complex compared to many other complex natural product isolated now, due to the lack of techniques, it took long time to arrive at its correct structure. Degradation studies were carried out to assign partial structure. So, this Pasteur group in 1853 demonstrated that quinine is levorotatory, and the empirical formula was demonstrated by Strecker group in 1854. And the degradation studies on quinine gave quinotoxin, meroquinine, methoxyquinoline derivatives. So the structure of quinine was discovered by Paul Robin, reported by Paul Robin 1907, and the first partial synthesis was reported by Paul Robin 1918, and the first formal synthesis was reported by Woodward Group in 1994, and the first stereoselective total synthesis was reported by Stokes Group in 2001. So this Woodward's formal synthesis use starting material metahydroxybenzaldehyde, and they use key reaction managed reaction, and he synthesized up to quinotoxin, which was already converted into quinine by Doring's group. So the Stokes first asymmetric total synthesis was completed in 13 steps with 18 percentage of overall yield. Now, the lecture 33 was about dendrobin. So, here this application of silver ion mediated cyclocondensation in the total synthesis of dendrobin by Livinghouse, radical cyclization in the total synthesis by Shah and Posenkand in reaction in the total synthesis of Zar. So, this is having 7 chiral centers, 6 of which are contiguous, and it is having 3 5-membered rings, one of which is a lactone and other substituted pyrrolidine. Then it is also having a 6-membered ring, and it is isolated in 1932 from Chinese ornamental orchid Dendrobium nobai. And the first, this Living House reported the total synthesis in 8 steps of this plus or minus dendrobin from 2-methyl cyclopen 2 in 1. And the key reaction involved silver ion mediated cyclocondensation of isonitrile with acyl chloride, and this was completed in 10 steps. So this Shah's total synthesis was done from starting material carbon, and in this synthesis, enantiomerically pure dendrobin was accomplished based on alpha carbonyl radical cyclization, and it was completed in 19 steps. So in SARS total synthesis, which was reported in 1999, it was a chiron approach from Verbinon, and they used a radical mediated ring opening and Poisson-Kant reaction to construct two five-membered rings, and they completed this total synthesis in 19 steps. Now, in the last lecture of week 7, we have seen this total synthesis of morphine, where we have seen the application of Diels-Alder reaction, Michael addition, and Woodward open or oxidation in the first total synthesis of morphine by Gates. So, this morphine was first isolated in 1806 from opium, which is produced by the cut seed pods of Poppy papaver somnifera. And it is having three six-membered rings, one dihydrofuran ring, five contiguous chiral centers, and this Robert Robinson in 1925 proposed its correct structure. Gates confirmed its structure by first total synthesis in 1952 by X-ray in 1955. And the natural opiates include morphine, codeine, thebaine, and oripavin. And Gates and Schudy reported the first total synthesis of morphine in 27 linear steps using open or oxidation as the key step, and they used Diels-Alder reaction also. They started with naphthalene 2,6-diol in their total synthesis. And it took 27 linear steps with 0.0010 percentage of overall yield. And in Obermann's total synthesis of morphine, which was completed in 1993, uh, they did this intramolecular Heck reaction to force the critical quaternary center of morphine skeleton, then sequential iminium ion allyl silane cyclization using starting material isovanilline. And they completed this total synthesis in 10 steps with 1.01 percentage of overall yield. So that was about the lectures in week 7. So now we will discuss some mechanisms of the reactions which were seen in this lecture. So the first reaction was Bischler-Napieralski cyclization. So it is basically the cyclization of this kind of amide. Okay, so it is basically used for the synthesis of this kind of dihydroisoquinolines from this beta ethyl amides of electron rich arenes, where mostly this POCl3 or P2O5 or zinc chloride is used. So as we can see this mechanism. So firstly, what is happening? This oxygen have an affinity towards this phosphorus. So this will attack over this phosphorus, and this nitrogen lone pair will come over here, and this will attack over this phosphorus to form this intermediate with a positive charge on this nitrogen. Then a removal of proton from this nitrogen will neutralize this positive charge on nitrogen to give this intermediate. Then again, what is happening? This nitrogen lone pairs will fall over this bond, and this group is leaving. So this POCl3 is getting eliminated to form this intermediate. Then what will happen? This will push. So this oxygen lone pairs of this O methoxy will push towards itself. This bond will migrate to here, and this will come and attack over this carbon. And this will shift over this nitrogen to stabilize this positive charge. So we'll be getting this intermediate. Then again this rearomatization will take place by removing this proton to give this compound. So this kind of cyclization is known as Bischler-Napieralski cyclization. So what is that? Basically the synthesis of this kind of 3,4 dihydroisoquinolines from beta ethyl of electron rich arenes. And for this condensation, so it is basically a condensation reaction, that is water is getting removed, and for this condensation reaction either POCl3, P2O5 or zinc chloride is being used. So I'll give you 2 minutes maybe to quickly go through the mechanism, then we will go to the next reaction. Okay, now the next reaction, intramolecular Heck reaction. So here what is happening, this coupling is happening between this halide and this alkene. So previously we have seen the mechanism for intermolecular Heck reaction, where an aryl halide and an alkene will be reacting to form the coupled product. So here it is having in the same happening in the same molecule in the presence of a palladium catalyst and a base. So the mechanism is same as that of intermolecular one. First, this active catalyst will be forming, that is this one. Then this oxidative addition will take place. Then this insertion, alkene insertion will take place, and then beta hydride elimination will give this product. So the next reaction is how. So I'm not going into the detail because we have previously discussed the mechanism of Heck reaction. Now the next reaction is open or oxidation. So it is the oxidation of alcohol with the help of this acetone and aluminum triisopropoxide to get this corresponding ketone, and this acetone will be reduced to the alcohol isopropanol. So the reverse reaction is known as mpv reduction, and this forward reaction is known as open or oxidation. So this is the mechanism. Firstly, this hydroxyl group will coordinate with this aluminum, and then this isopropoxide ion will leave from this aluminum triisopropoxide, and this whatever left isopropoxide ion will take this hydrogen from this alcohol to form this intermediate. Then this oxygen lone pairs of this acetone will attack over this aluminum to form this intermediate, and that will form this six membered chair like transition state, and then this will leave and this will be forming. So again, hydrolysis will give this isopropanol and this oxidized product. So if it is reverse it is happening, it is known as mpv reduction by using same aluminum triisopropoxide. Now the next one is MPV reductions, that is Mervyn pond of Worley reduction. So that is the reverse of open or oxidation, and this is the mechanism. You may quickly go through it. I am not going into the detail. The mechanism is exactly the opposite of what we told in this open or oxidation. Okay, so the next reaction is managed reaction. So the managed reaction also, I think we have previously discussed in the last class also. So it is a condensation reaction between aldehyde or ketone in the form of an enol with an iminium ion producing beta amino alkyl carbonyl compounds. So here, as we can see, there is a ketone and aldehyde and secondary amine in the presence of acid, and then in the second step, in the presence of a base and hydrolysis, we will be getting this beta amino alkyl carbonyl. So here, this formaldehyde is used mostly often due to its higher reactivity, and this works only with primary and secondary aliphatic amines. Aromatic amines will not be reacting. Yeah, so this mechanism we have already discussed in the last class, so I am not going into that. Maybe you can quickly go through the reactions and the lecture contents which we discussed, then we will move on with the discussion of week 6 assignment. So, moving to the week 6 assignment, this is the first question. Identify the major product in the following transformation. So, this particular compound, upon treatment with this paranitro, this acid, and this sodium bicarbonate in chloroform, which will be the major product here. So this is the correct answer. So what is happening? Firstly, this peroxy acid like MCPBA. So MCPB is metachloroperbenzoic acid. This is para-nitroperbenzoic acid. So that will form epoxide. And then what is happening? This lactone, this oxygen will attack over this position, and this epoxide will open to form this product. So the correct answer would be option D. Now the next question, what is the major product formed in the following transformation? So this compound upon treatment with first NOCl and pyridine, then HNU, and then hydrolysis, which will be the major product. So here the correct answer is, firstly what is happening, this NOCl will form this ONO with this hydroxyl group. Then under HNO condition, that NO bond will cleave and O radical will be formed. Then this hydrogen radical will remove, and that radical will combine with that NO radical to form this compound, to form this. So this radical will be formed, and that will combine with NO radical to form this one. Then what is happening, this hydrogen abstraction would take place to get this intermediate, and then that on hydrolysis will give this compound. So the correct answer is option D. So this is written like this. Okay, now the next question, identify the major product in the following transformation. So, this hydrazine, upon treatment with this aromatic compound in the presence of polyphosphoric acid, which will be the major product here. Okay, so here the correct answer is option D, and this what is happening. This we have seen the mechanism. So this is like Fisher indole type of synthesis, and this indole ring will be formed. So the correct answer would be option D. Now the next question, which is the major product formed in the reaction given below? So this diol upon treatment with this H2SO4 in acidic condition, which will be the major product formed here. Okay, so this is an example for this kind of reaction. So what is happening in the presence of H plus, one of this hydroxyl group gets protonated, and that will, like, this one of this group will migrate to this center, and this bond will shift over here to form this compound. So if this phenyl group is migrating, it will form this product, and this bond is migrating, that will give this product. So here what is happening, this is major product, so this is having the more migration capability than the phenyl ring, so this that will form this option C. Now the next question, identify the reagents causing the following transformation. So this particular compound is converted into this one, so which of this reagent combination can give in exact sequence this product. So here four options are given, and here, so out of this four options, which will be the correct combination of reagents that can give this corresponding product. So here the correct answer is option C. So first, what is happening with this allene? It will first undergo under H nu condition this photocycloaddition 2 plus 2 cycloaddition to get this four membered ring, and then ozonolysis of this double bond will give this compound. Now the next question, identify the reagents causing the following transformation. So here this is like substitution of this group over this position. So for that, which will be the reagents needed? So here what is happening? Firstly, we have already seen this Fischer-Indolls, and this is for the formation of this ring. So once this is formed, then the CH2NMe2 can, so that is CH2O, and this dimethylamine that can form this intermediate, that will form this intermediate, and then in the presence of methyl iodide it will form this uh, NMe3 plus, then NaCN will substitute it with the Cn, then LAH will reduce it to form this NH2. So that's how this compound is made. So firstly CH2O and Me2NH will substitute it with this here CH2NMe2, then methyl iodide will methylate that again to form this NMe3 plus, then NaCN will substitute it with Cn, and then LAH will reduce that into CH2NH2. So that's how this is formed, and the correct option is an option. Correct answer is option C. Now the next question, identify the major product formed in the reaction given below. So this iodoaniline and this compound upon treatment with this uh, formaldehyde in heat, we will be getting one product, and which can reversibly give the starting materials in by treating with aqueous HCl. So out of this four options given here, which will be the major product? So here what is happening, this is the correct compound. So this is like a condensation reaction, we can say. So with this aniline, this amine group that is undergoing this condensation kind of reaction to form this intermediate. So this CH2 is coming from this formaldehyde, so imine formation, and then this will attack over that carbon to form this one. So the correct answer is option C. Now, the next question, identify the major product in the following transformation. So, this compound, upon treatment with this acetaldehyde in acidic condition and heating, which will be the major product here? So, here the correct answer is this one, option A. And here, what is happening with this MECHO? Firstly, this imine formation will take place, and then cyclization and migration of the double bond will take place, and then hydrolysis will be giving this product, option A. Now the next question, identify the major product of the following reaction. So here this compound upon treatment with this TMSCl and sodium iodide, which will be the major product here. So here the correct answer is option B. And what is happening? Firstly, this nitrogen lone pair will attack over this TMS and the Cl minus will leave to form this compound. Then I minus will attack over the cyclopropane ring. This bond will shift over here and this will stabilize this positive charge on nitrogen to form this intermediate. Then again this nitrogen will attack over this carbon and this iodide will leave to form this compound. So the correct answer is option B. Now, the last question of week 6 assignment, identify the major product in the below reaction. So, this compound upon treatment with this aluminum trichloride in benzene, which will be the major product. So, here four options are given, and the correct answer is option C. And what is happening in this reaction is, firstly, with this is the product. So, just this ring will open and this Friedel-Crafts cyclization we can say, and that will be giving this, like this cyclization at this position, this will open and cyclization will Friedel-Crafts acylation kind of reaction in the presence of AlCl3, that will be giving this option C. So that's all about the week 6 assignment. Now moving on to the lecture, week 8 lectures. That was firstly about this morphine. So where we have seen the application of tandem cyclization of an ortho allyloxy aryl radical. Allelosy aryl radical, Mitsunobu reaction, Beckmann rearrangement, and carbenoid CH insertion in the total synthesis of morphine by Parker and White group. So Parker's approach towards the cyclization of morphine ring system was based on a tandem cyclization of an ortho-allyloxy aryl radical. And the Parker reported a short 11 steps conversion and stereospecific synthesis of plus or minus dihydroisocodeine, which on oxidation completes the formal total synthesis of morphine. The starting material used were isovanillin and metamethoxyphenethylamine. And the key reaction involved Mitsunobu reaction as well. This was reported in 1992 in 11 steps with 11.63% of overall yield. Now, in White's total synthesis, which was published in 1997, their focus of synthetic work was unnatural enantiomer, that is plus morphine. And the carbenoid CH insertion was a key step using the starting material isovanillin. And another key reactions were stop condensation, Robinson annulation, and Beckmann rearrangement. And they could complete this total synthesis in 28 steps with 3% of overall yield. Now, in the next lecture, we have seen the total synthesis of methyl homo secodafniphyllate and secodafniphyllate, where we have seen the application of sequential 1,4 addition of enolate derived from an amide to an alpha beta unsaturated ester, followed by quenching with allyl iodide as one of the key reactions to get the key precursor in the total synthesis of methyl homo secodafniphyllate and secodafniphyllane by Heathcock. So, these are squalene derived natural products. And coming to methyl homo secodafniphyllate, it is isolated from the barks and leaves of Eusoria, and it is used in the treatment of asthma. The main challenges were highly congested pentacyclic skeleton as shown in the figure, and it is having 8 contiguous stereogenic center and 2 contiguous quaternary centers. And in Heathcock's total synthesis, which were including both racemic and asymmetric total synthesis, the key reactions were intramolecular Diels-Alder reaction and Asaprin's reaction. Now coming to secodafniphyllane, which is having an additional bicyclic group. The starting material used was propanol, and the key reactions were Cannizzaro reaction and Zipper reaction. So Zipper reaction is basically the isomerization of internal alkynes to terminal alkynes. Now, for this lysergic acid, we have seen the application of Friedel-Crafts acylation, aldol condensation, intramolecular imino-Diels-Alder reaction in the total synthesis of lysergic acid by Woodward and Opelzer. So, these compounds belongs to ergot alkaloids, and it was first used as a drug for the treatment of migraine. The tetracyclic core structure with the intol as their core is responsible for its biological activity. So LSD is a most potent psychoactive agent discovered in 1943 by scientists from Sandoz with psychoactive effect. And the first it was synthesized in 1938 by Albert Hofmann during purification in the final step. This was interrupted by some unusual sensation. So LSD is a derivative of lysergic acid. And Woodward's total synthesis is the first total synthesis of this lysergic acid, which came in 1956. And the starting material used was indole 3 propionic acid, and the key steps were Friedel-Crafts acylation and aldol condensation. And they completed this in 15 linear steps with 0.78% of overall yield. Now, in Opelsa's total synthesis, which was reported in 1981, the intramolecular immunodisulfide reaction was the key steps, and the starting material used was 4-hydroxymethyl, 1-tosylindole, and they completed this in 9 steps with 3.88% of overall yield. Now coming to galantamine, there we have seen the application of oxidative phenol coupling, crystallization induced chiral conversion, palladium catalyzed asymmetric allylic alkylation, intramolecular Heck reaction in the total synthesis of galantamine by Barton, Jordis and Trost. So this is structurally similar to morphine. The parent member of galantamine type amyloidaceae alkaloids, and these are isolated from Galanthus voronovi. It is used in the treatment of Alzheimer's disease due to its selective acetylcholinesterase inhibition. And this Barton and Corby's total synthesis was the first total synthesis, which was published in 1960, where the oxidative phenolic coupling was the key step to connect the aromatic rings in a biomimetic way. And the starting materials used were isovanillin and parahydroxyphenylacetic acid. They completed this total synthesis in 7 steps with 0.53% of overall yield. Now, in Jorda's total synthesis, which was a multi-kilogram scale synthesis reported in 1999, the starting material used was dimethoxybenzaldehyde, and the key steps involved oxidative phenolic coupling, crystallization-induced chiral conversion of plus or minus narvadine to minus narvadine, and they completed this total synthesis in 9 steps with 12.4% of overall yield. And this is a practical and cost-effective synthesis to pilot, plan, scale up for clinical trials. Now, in Trost total synthesis, which was reported in 2000, the key steps were palladium catalyzed asymmetric allylic alkylation and intramolecular Heck reaction. The first total synthesis were oxidative phenolic coupling, and uh, this is the first total synthesis where oxidative phenolic coupling was not used, and the starting material used here is isovanillin, and they completed this total synthesis in 17 steps with 1.13% of overall yield. Now, the last lecture of week 8 was epibactidine. There we have seen the application of reductive palladium catalyzed Heck type coupling, microbial oxidation, palladium catalyzed desymmetrization of cis 3,6 dibenzyloxy 2 cyclohexene, and a palladium catalyzed cross coupling, fluoride promoted fragmentation, and Hoffman rearrangement in the total synthesis of epibactidine by Regan, Olivo, Trost, and David A. Evans. So this was isolated from Uradoran poison frog Epipedobatis tricolor, and it contains chloropyridine, and it appears to be unique in possessing the 7-asa bicyclo 2 to 1 heptene ring system. And its analgesic activity is 1 by 200th dose of morphine. Now, in Regan's total synthesis, which is a racemic synthesis, it was reported in 1993, where they have utilized this concise, highly convergent, and completely stereoselective for the desired exoisomer. And the key step was reductive palladium catalyzed Heck type coupling using the starting material pyrrole and 2-aminopyridine with 25.9% in 2 steps. And in Olivo's total synthesis, which came out in 1999, which was a biocatalytic approach, the starting material used was hydroxycycloaminohexane, and the key steps involved intramolecular nucleophilic displacement of the starting material, microbial oxidation of unfunctionalized carbon, and coupling of chloropyridyl ring to a 7-asa bornate. Overall yield is 8.11%. Then in Lay's total synthesis in 1999, 10 steps using an organized array of polymer supported reagents and sesquiterring agents in a successive manner. Here in this total synthesis, no chromatographic purifications are required to afford the product in greater than 90% purity. And they completed this in 10 steps with starting material 6 chloro nicotinoyl chloride. And they utilized intermolecular Diels-Alder reaction also in this total synthesis, and it was completed in 32.45% of overall yield for plus or minus exoepibattery. Now, in the TRAW synthesis, which was published in 1996, which is the first asymmetric total synthesis, the palladium catalyzed desymmetrization of cis 36 dibenzyloxy 2 cyclohexene and palladium catalyzed cross coupling were the key reactions. And the starting materials used were cyclohexadiene. In 10 steps, 13.36% of overall yield they could get. Kobayashi's asymmetric synthesis was published in 1998, where the key steps were asymmetric heterodyl-Salda reaction. And this total synthesis was completed in 9 steps with 3.6% of overall yield. So that was about week 8 lecture contents. Now we have to discuss some of the reactions which were discussed in the week 8 lectures, so that we will continue in the next class, followed by the discussion on week 7 assignment. So if you have any queries regarding today's lecture, please do let me know. Thank you for joining and thank you for listening. Thank you. See you in the next tutorial session.